Welcome, everyone. My name is Khaldoon Ghanem. I'm a senior DevTech engineer at Nvidia, focusing on quantum computing. The focus of this talk is on state vector simulations, which remain the dominant tools for simulating quantum circuits at the logical level. My goal is to give you a high-level understanding of how these simulations are implemented on the GPU, so you understand the performance limiters and how they affect the scaling of these simulations. Let me start by motivating why do we need to simulate quantum computers. On the one hand, simulating quantum computers on the physical level allows hardware researchers and designers to explore ideas, model qubit interaction, and test system designs efficiently and cheaply in software before committing to expensive hardware. On the other hand, simulating quantum circuits at the logical level enable quantum algorithm research and development. At this early stage, this simulation remains the primary tool for testing, validating, and debugging quantum algorithms where quantum computers are still limited in scale and noisy. Additionally, simulation is an invaluable educational resource for teaching quantum computing concepts, which can be complex and difficult to comprehend for newcomers. So simulation provides a tangible way for learning these concepts. Now, why would you want to use GPUs for these simulations? First, quantum simulations are highly computationally intensive, and GPUs are designed for massive parallel computation. They can perform thousands of operations at once, making them ideal for the kind of linear algebra and tensor operations at the heart of quantum simulations. Also, as we'll see later, this simulation requires exchanging large amounts of data within the processing unit and between units. And GPUs provide a high bandwidth memory access and high bandwidth for communication between GPU via, for example, NVLink. The third reason is about energy efficiency. Compared to CPUs and large clusters, GPUs provide a better performance per watt. Also, recently, there is a growing ecosystem of GPU-accelerated libraries like Nvidia CUDA-Q framework and cuQuantum SDK. These libraries are built to take advantage of the GPU performance, and they take away much of the complexity in building high-performance quantum simulations on the GPU. Here is an overview of Nvidia platform and the different simulation options it provides for different users. At the foundation, we have cuQuantum SDK, which provides different low-level APIs for accelerating quantum simulations. It provides cuTensorNet and cuStateVec APIs for simulation of quantum circuits at the logical level. It also provides the cuDensityMath API for simulating quantum hardware. Generally, the audience of cuQuantum SDK are developers of quantum simulation libraries like Cirq, Qiskit, Qtip, and many of the other libraries who already adopted cuQuantum as an accelerated backend. For end users, we have at the top CUDA-Q, which targets quantum researchers. These are researchers working on developing quantum algorithms or designing quantum hardware. CUDA-Q is a high-level simulation framework accelerated by cuQuantum, like the others mentioned here. But it also stands out because it provides a single quantum classical programming model, so the user can write a hybrid quantum classical program once and run it anywhere, either on GPU through simulation or any on the supported quantum vendors. Since the focus is on state vector simulation, the relevant part of this stack is the cuStateVec component of cuQuantum and how it's utilized within CUDA-Q. So let's quickly review what we are trying to simulate with state vector simulations. What we are trying to simulate is the output of a quantum circuit. And as you already know, a quantum circuit is basically a bunch of quantum gates applied to a specified set of qubits. And these qubits usually act on single qubits or a pair of qubits. And higher qubit gates exist and used, but they are used less often. At the end of a circuit, we measure the qubits, and because of the measurement, the quantum state collapses, and we get a random bit string. The goal of the simulation is to predict the quantum state at the end of a circuit, and use that to either directly sample the bit strings or, in some cases, calculate certain interesting expectation values. Mathematically, the state of a quantum circuit is a complex linear combination of all possible bit strings. And state vector simulation take a direct approach at this by representing the state with a vector with 2 to the power of n complex numbers. So for a 2-qubit state, that would be 4 numbers corresponding to the bit strings 0, 0, 0, 1, 1, 0, and 1, 1. Each of these numbers is called an amplitude, and its magnitude squared represents the probability of measuring the corresponding bit string. Now, it's important to note here that which bit string an amplitude corresponds to is implicitly encoded in the location of the amplitude within the state vector. So for example, the amplitude C2 corresponds to the probability of measuring the bit string 1, 0, because 1, 0 is a binary representation of its index 2. With this representation, we see one of the challenges of state vector simulations, namely the exponential memory requirements. In order to store the state of n qubits, we would need 2 to the power of n plus 3 bytes of memory, and that's using single precision, and double that for double precision. Similar to how states are represented by vectors, gates are represented by matrices, and a gate on n qubits would be represented by 2 to the power of n times 2 to the power of n matrix. So for example, a 1-qubit gate like the Hadamard gate would be represented by a 2x2 matrix, while a CNOT gate, which is a 2-qubit gate, would be represented by this 4x4 matrix. Now, having defined the representation, performing state vector simulations conceptually is pretty straightforward. We first initialize the state vector to the desired initial quantum state, which is usually the all 0-bit string, and then we apply the gates one by multiplying the state vector with a matrix corresponding to the gate. And at the end, we convert this state vector into a probability distribution and sample it with some discrete sampling method. Now, I can already hear some of you complaining, how can we, for example, apply a 1-qubit gate, which is a 2x2 matrix, to a 10-qubit state, which we said is represented by a vector with 2 to the power of 10 elements. The dimensions do not match. The missing piece of information here is that the applied matrix is formally not the gate matrix itself, but rather a tensor product of the gate matrix with identity matrices on all the qubits that the gate does not apply to. So for example, if we're applying a Hadamard gate on the first qubit of a 2-qubit state, then the applied matrix would be this tensor product producing a 4x4 matrix of the correct size for this 2-qubit state. Of course, the order in tensor products matter, so applying a Hadamard gate to the second qubit would be a different tensor product producing a different 4x4 matrix. Already with this small example, you see that the matrix has a lot of zeros. And the number of those zeros will grow exponentially with the number of identity matrices in the tensor product. In other words, in the number of the skipped qubits that the gate does not apply to. So it would be naive to explicitly construct these huge sparse matrices in memory and directly work with them. What we do instead is take advantage of the regularity of the sparsity, and we convert this huge sparse matrix vector multiplication into many independent smaller matrix vector multiplications. In these smaller dense multiplications, the gate is now the gate matrix itself, and the vectors are subvectors of the full state vector. Generally, when we are applying an m-qubit gate, then the matrix will be 2 to the power of m times 2 to the power of m matrix, and the vectors will be, the subvectors will be vectors with 2 to the power of m elements. So the dimensions match, and we will have 2 to the power of n minus m of those subvectors. Each subvector will be composed of amplitudes whose indices differ exactly by m bits. And those bits are the qubit that the gate is being applied to. Let's look at a few examples. Let's say we have a 3-qubit state vector, and we want to apply a 1-qubit gate to it. Then the full state vector has 8 elements, and we will divide it into 4 subvectors, each of 2 elements. Now, which element constitute each subvector will depend on which qubit the gate is being applied to. If we are applying it to the first qubit, for example, then the subvectors will be composed of amplitude whose indices differ by the value of the first bit. So the first subvector will be composed of amplitudes 0 and 1, the second one with amplitudes 2 and 3, and so on. However, if we're applying this gate to the third qubit, then the subvector will be composed of amplitudes which differ by the value of the third bit. Therefore, amplitude 0 will be coupled with amplitude 4, and 1 with 5, and so on. For larger gates, the same idea applies. For example, if we have a 2-qubit gates on the first and the third qubits, then we will have now 2 subvectors, each with 4 elements. And the first of those subvectors for this specific case will be amplitude 0, 1, 4, and 5, and the rest will constitute the second subvector. Implementing gate application this way on the GPU is a matter of launching a CUDA kernel with as many threads as the number of subvectors, and then letting each thread perform the dense matrix vector multiplication independently. And implementing such a CUDA kernel correctly is not that difficult for anyone with a basic familiarity with CUDA. But obtaining the top performance on modern GPUs is a much trickier task. And that's where cuStateVec library can help. It provides a highly optimized API for gate application. These optimizations range from hardware-specific optimizations, like utilizing tensor cores and shared memory, to high-level ones, like special handling of control qubits and diagonal gates in order to reduce the overall computation. cuStateVec also facilitates the idea of gate fusion, which I will shortly talk about, and does this by supporting gate application with arbitrary size and automatically selecting the best CUDA kernel implementation depending on the size of the gate and on the architecture of the GPU you are running on. Now, what is this gate fusion and why do we need it? The problem is that many circuits are mostly specified in terms of 1 and 2 qubit gates. And these low qubit gates have small matrices, which means that the gate application kernel will have a low arithmetic intensity. This low arithmetic intensity basically means that we have a relatively low number of floating point operation per byte read or written to memory. Such kind of calculation is called memory bound because it will be limited by the bandwidth of the memory of the hardware. And if we don't do anything about it, then state vector simulations won't take advantage of the full power of the GPU. We won't saturate the maximum flop of the GPU. The solution to this is gate fusion, where we combine neighboring gates on neighboring qubits into larger gates. And the maximum size of a fused gate is a parameter of this technique. Using gate fusion, we'll be able to speed up the calculation by reducing the overall number of calls to gate application kernels, and at the same time, increasing the arithmetic intensity of each gate application. This technique is implemented in CUDA-Q. It's in Nvidia backend, which is a cuQuantum-based state vector simulator. Here's an example in CUDA-Q. I generated a quantum volume circuit on 32 qubits with 30 layers. On the x-axis, I varied the gate fusion parameter. And on the y-axis, plotted the actual number of gate applications for each value of the gate fusion parameter. Originally, the circuit had 480 gates. And you see, as we increase the gate fusion parameter, the number of gate application goes down almost proportionally. So that would suggest that always more gate fusion is better, right? Well, not so fast. Let's look at the run times. Here, I run this circuit on H100 GPU. And I did that in single precision, plotted the result in green, and double precision, and plotted that in red. Initially, as expected, we see that the runtime goes down as we increase gate fusion, but only up to a certain point, 5 for single precision and 6 for double precision. Beyond that, the runtime starts increasing again, which can seem surprising because we just saw in the previous plot, even beyond that point, the number of gate application was going down, and we say the arithmetic intensity is also going up. So why is the runtime increasing? The reason is that gate fusion also increases the total amount of flops that needs to be done because we have larger matrices. However, this increase in flops is not a problem at all as long as the computation remains memory bound. But once we are saturating the maximum flops of the GPU, then this increase in flops will increase the runtime. When it was a memory-bound computation, this increase in flops is exactly canceled by the increase in its arithmetic intensity. But beyond that point, we will see an increase in the runtime. Therefore, the gate fusion parameter depends on the characteristic of the hardware, most importantly on the memory bandwidths and the maximum flops of the GPU. In CUDA-Q, this parameter is set automatically depending on the GPU architecture. And this way of setting this gate fusion parameter works extremely well in most cases. In some cases, you may want to deviate from the default value, and CUDA-Q offers the option of doing that with an environment variable. Now, having optimized kernels and using gate fusion with an optimal gate fusion parameter, how much speed up should we expect a GPU to show compared to a CPU for state vector simulations? Generally speaking, GPU will outperform the CPU for simulating circuits for around 20 qubits and more, and the speed up will increase with increasing number of qubits. Here, I compare the performance for simulating a quantum Fourier transform circuit using CUDA-Q on a Blackwell GPU versus Qiskit on a high-end 128-core CPUs. And we see already at 22 qubits, we have a speed up of around 10x for single precision and double precision. And that speed up increases at 30 qubits to more than 60x for double precision and more than 80x for single precision. The discussion so far has been about single GPU simulations. Now I want to talk about multi-GPU simulations. The obvious reason for using multiple GPUs is to reduce the runtime. But the more important critical reason is enabling the simulation of circuits with a large number of qubits. The largest number of qubits you can simulate on a single GPU is limited by its memory. And currently, the largest available GPU memory is 192 gigabytes, which can accommodate at most 34 qubits in single precision. If we need to go beyond that, we need to combine the memories of multiple GPUs. In these multi-GPU simulations, the full state vector is divided equally among the available GPUs, which for simplicity we'll assume is a power of 2. And typically, each GPU is associated with an MPI process, and communication happens via MPI, and in some cases with CUDA IBC. Now, let's assume we have 2 to the power of G GPUs. Then we can view the n bit representation of a full state vector index as a concatenation of 2-bit strings. A top part composed of G bits, giving the index of the GPU, and a bottom part of n minus G bits, giving the index of the amplitude locally within a GPU. We call the top part global bits or qubits, and the lower part local bits or qubits. Here's an example of a 5-qubit state vector divided among 4 GPUs. In this case, since we have 4 GPUs, we'll have 2 global bits, which is the binary logarithm of the number of GPUs, and the rest will be local qubits. Notice here how GPU 0 holds all the amplitudes whose top 2 bits, the global bits, are 0, 0, because that's the binary representation of the GPU index 0. While, for example, GPU 2 holds all the amplitudes whose top 2 bits are 1, 0. And the rest of the bits, they are increasing incrementally within each GPU. That's why we say that the global bits are indexing the GPU, and the local bits are indexing the amplitude locally within the GPU. Now, this division of bits or qubits into local versus global is very useful because it turned out that applying a gate to a local qubit doesn't require communication between GPUs. Remember, we just said that gate application translates into many independent matrix multiplication with subvectors. If this gate is applied to a local qubit, then each subvector will be contained entirely on a single GPU. So no communication is needed to apply that gate. Only if this gate is applied to a global qubit, then the subvectors will be distributed on different GPUs and communication is required. Here are concrete cases using the previous example. Let's say we want to apply a Hadamard gate to the first qubit, qubit 0, which is a local qubit. Then the subvectors will be composed of amplitudes whose indices differ by the value of the first bit. That means that each GPU can apply the Hadamard matrix to its own amplitudes without needing amplitudes from another GPU. While if we want to apply the same gate to the fourth qubit, qubit 3, which is a global qubit, then the subvector will be composed of amplitudes whose indices differ by the value of the fourth bit, and those reside on different GPUs. So GPU 0 would need amplitudes from GPU 1 and vice versa. Similarly, GPU 2 and GPU 3 would need amplitudes from each other. So in general, if you want to apply a gate to a local qubit for multi-GPU simulation, the implementation goes exactly the same way as in a single GPU implementation, just repeated on multiple GPUs. But if you want to apply it to a global qubit, then some extra work is needed. A simple way of achieving this is first let each pair of GPUs exchange the required amplitudes so that each subvector resides entirely on a single GPU. Then each GPU apply the gate locally as before, and once we are done, we move the amplitudes back. Here's an example for applying the gate to the global qubit 3. Then GPU 0 and GPU 1 will exchange half of their amplitudes. Similarly for GPU 2 and GPU 3. Then each GPU execute the gate application kernel independently. And once they are done, they move the amplitudes back. Now with this approach, you see we need to exchange the amplitude twice for each gate application. Once before and once after each gate application. But we can do better, cut the communication time in half and avoid the later exchange by a simple observation. This observation is that each of these amplitude exchange is equivalent to swapping a local qubit with a global qubit. So instead of doing the later exchange, we give the qubit labels, and then we keep track of the location of each qubit after each exchange. So in this improved approach, instead of after doing the exchange, the first exchange, we note somewhere that this exchange, in this specific case, is equivalent to swapping qubit 0 with qubit 3. Now qubit 0, which was a local qubit, now became a global one. And qubit 3, which was a global qubit, is now a local qubit. And this, since qubit 3 is a local qubit, then we can apply the gate kernel directly on each GPU locally without communication. If we later encounter another gate on qubit 3, no communication is required because qubit 3 is already local. Only when we encounter gates on one of the global qubits, which at this point became qubit 4 and 0, we need to swap them with one of the local qubits in order to be able to apply the gate to them. This same idea can be generalized to multi-qubit gates. In general, we can swap simultaneously k pair of qubits. And in that case, the GPUs will be divided into groups of size to the power of k. And then each GPU will exchange 1 over the power of k of its amplitudes with each of the other GPU within the group. Here is an example of swapping global qubits 4 and 3 with local qubits 0 and 1. As you can see, the goal of this chart is not the specifics, but to show you how it can get pretty complicated figuring out where each amplitude should go with these multi-qubit swaps. And that's where statevector can be enormous help again to simulation library developers. It provides an API that facilitates qubit swaps. It provides optimized primitives for swapping qubits within a node using CUDA IBC, allowing for peer-to-peer communication so that the data can be accessed directly from one GPU into the other. It also provides a more general communication mechanism via MPI that allows for intranode and internode qubit swaps. Recently, cuQuantum added the cuStatevector X API, which encapsulates a lot of the common tasks that happen in these kind of simulations. And these higher level primitives make designing these simulations even easier. For end users, CUDA-Q already have a multi-GPU, multi-node backend based on cuQuantum. This backend is optimized to take the fastest communication path between GPU given a network topology. It also performs gate grouping and fusion in a way that minimizes qubit swap in order to reduce the communication overhead. And this communication overhead becomes indeed the bottleneck for these multi-GPU simulations, because each of these qubit swaps exchange almost entirely the state vector between the GPUs, and happen that multiple times during the simulation. So the bandwidth of the interconnect between the GPU plays an important role for the runtime of these simulations. Here I compare the runtime for quantum phase estimation circuit running on a single node with 8 H100 GPUs. And I use different communication paths. And you see, using NVLink, the runtime is about 2.5 faster than using PCI Express, because NVLink provide a much higher bandwidth. And even though in this case, the PCI Express was allowing for peer-to-peer communication. If we were to disable that, where on some platforms peer-to-peer communication is not available, then the simulation would run an extra 2 times slower, because then the data needs to be staged through temporary CPU buffers. This shows that these for this kind of simulations, how the GPUs are communicating plays an important role in the scaling of these algorithms. This is even more pronounced when we compare the performance of multi-node simulations. For example, here I compare the performance between InfiniBand network, which until recently was the fastest, highest bandwidth interconnect you can get between nodes, and I compared with the recently developed multi-node NVLink. Here I run the same previous circuit on a GB200 NVL72 system, which is a multi-node system. And we see as we increase the number of qubits from 36 to 39, running on an increasing number of nodes, up to 16 nodes, each with 4 GPUs. Multi-node NVLinks provides a huge speed up compared to InfiniBand, running up to 6 times faster on the largest qubit count. This again shows that the network becomes the bottleneck for these large-scale state vector simulations. And using a high bandwidth interconnect like multi-node NVLink is critical for obtaining good performance. With this, I come to the end of my talk. To summarize, we looked into the basics of how state vector simulations work on GPU. We saw that these simulations are basically memory bound, but we can circumvent this issue with gate fusion. We looked into how to extend a single GPU simulation into multi-GPU one via the idea of qubit labeling and swaps. And we saw that these swaps require exchanging a large amount of data, so using a high bandwidth interconnect become important. Along the way, I highlighted some parts of the Nvidia platform that's relevant both to simulation library developers and to end users. Thank you for your listening.
Thank you very much. Thank you.